Okay, we're back. Thanks for your indulgence last week when I was kind of a little out. It's sort of settled in my throat. I'm not contagious or anything. It was not COVID. I tested for that, but it settled here and kind of turned me from a tenor into a baritone. So get my Barry White voice going or something. Um, okay. So we are, let's see. No, that this is so weird. Okay, so I guess I'll just have to do it with. Okay, can everybody see this? Okay. Um, so what we're doing is we're modeling things that that move around. Again, doing it in the simplest possible manner. We ended last time with a numerical example for this, and so I want to use that to test out how the implementation is, because you might be feeling a little skeptical about this, or maybe you're just kind of pressing the I believe button, or maybe it all makes sense to you. But in any event, I want to kind of show you how to do that. Why? Because just as I talked about last quarter in the just even when you're doing programming, you want to be scientific about it, not in the computer science way, because computer science is an oxymoron. I mean, computer science isn't science, any more than political science is science. I mean, chemistry is science, physics is science. I mean, those other things. I mean, just because you call it science doesn't make it science. So what I mean about being scientific about it is forming a hypothesis about a specific outcome of an experiment, performing the experiment is running the program, and then testing it against your hypothesis. So if, in this case, we had a numerical example based upon just modeling a simple maneuver, in that this is the building block of what we're building up to. So in a two-dimensional space, we're just modeling this thing. You start at one place, you move to a specific destination at a constant velocity. And the question is, well, how can we implement that in our discrete event way? You're probably familiar, I mean, if you've done any stuff in animation or agent-based modeling, with the time step approach. And that's the advantage of the time step approach is that it's very simple, it's easy to understand, and there are a lot of, we'll just say, very bad properties about it. Not the least of which, as you recall, was the fact that if you want to get to a particular specific location at a specific velocity, then in a time step world, the chances are you can't do that. You can't get to that specific location. And then what these models do, and this is from experience, actual sort of models that are out there, they start putting band-aids on. You say, well, we can fix that, so every time we take a step, we kind of look to see whether a full step will take us past that, or then well, we went past that, so we have to take a back step and and whatever, and those have problems as well. In fact, the problems with time step are even worse than that, because depending on the size of the time step, you can get completely different answers, not just numerically different answers, but qualitatively different answers. If you've ever, have you ever studied numerical differential equations? Numerical solutions? No, I'm getting blank stares here, so, okay, well, never mind. Okay, so enough of sort of bashing time step. I'll try to not do that too much, but it's just that the okay, so our way of modeling it was the simplest mover was which is this on the right, was just to do that maneuver. We have the move to, we start move, and then we end move. And the idea is all the action happens here in this start move event, where we compute the velocity based upon how far we have to go. Not just how far we have to go, but what the relative direction that we have to go in, and what our speed is. So we turn the direction vector into a unit vector, multiply it by the speed, and we get the velocity. And then even without the velocity, knowing just the distance and the speed, then we can compute the time between when we start and when we end, moving it at a constant speed, so we can schedule this event. And the irony, to me, is that because location cannot be a discrete event state. Why? Because the location is continuously changing as you're making this maneuver, and discrete event states have to be constant. So how can you, and so the pushback from the time step folks is, well, since location cannot be a discrete event state, you can't model movement using a discrete event approach. And the irony is that you can model movement more precisely using this approach, because you can capture the location at any arbitrary time using the equation of motion. And okay, so we did a numerical example for it. So we had a mover that was 20 minus 30, and at time 0, it started moving to this destination at a speed of 30. So when we worked it out, it turned out to be, this thing, which was approximately, minus 10 something and 28 something. When did it arrive at the destination? Again, the exact, the left-hand side is the exact, and then whenever you're doing numerical calculations, it's always best to carry infinite precision as long as you can, and only round off at the very end. Why? Because if you round off too soon, those round off errors can start to build up, so that your ending answer is actually can be way off. And then finally, where, okay, so here turned out that it took like 2.8 some time units. And so we say, well, where were you at time 2? And so we can use the equation of motion for the numerical case to get that. So before charging ahead, let's test that out. Again, this is the scientific thing. So here, assuming that our math is correct, and I'm pretty sure my math is correct because I actually did it in my office and not in front of you. So I'm pretty sure this is correct. And then, as we saw, we implemented it in there's a Java one, there's a Python one. If I have time, I'll kind of demonstrate this in both. So I'll do the Java one first, because there are more Javas, and the Python people will have to, follow along. Because if you're a Python person, you might want to consider learning Java. And if you're a Java person, you might want to consider learning Python. I mean, Python is, especially if you're into like machine learning and things like that, data analysis, data science stuff, Python is the tool of choice there. So it's not that one is better than the other. It all depends on the task. Anyway, so let's check. We have the mechanism to do this. We have our simplest mover, and then now by itself, it can't really do anything. It has to be directed by another component, and we have a path mover manager. We can set a path mover manager, give it the destination, run it in verbose mode, and just check the values. And that way we can answer, at least check questions 1 and 2. What is the velocity? Because velocity was a state, and it's going to fire a property change whenever the velocity changes, if we do it right. And then if we just listen to that with one of our, with a simple property dumper, it'll print it out, and then we can compare it with the value that we computed. And then we can look for the end move event, and will that occur at the right time? Now, question 3, we're going to have to do a little bit more work on. But let's come to that when the time comes. So let's where are you? Come on. Go for this, because very annoying that it, just for those of you remotely, when I share the screen, but I'm in presentation mode in PowerPoint, it doesn't show. It only shows still shows the PowerPoint. Okay, so we have our simplest mover. I was able to to comment it a little bit. So let us do this. So let's do the check mover class. So, okay, this is the Java. And so our initial location was, what was it? It was 20 minus 30. Fix our imports. 20 minus 30. And for those of you who, just as a reminder, and for those of you who may not have had the Java class with me, whenever I write a double value, I always put the decimal point in, even if there's a 0, just to make it clear that that's what I intended. And the speed was 30. So our mover there, and then before doing anything else, always again, and just the way that I'm doing this is I'm doing this like one step at a time. I write a little bit of code and always test it. Okay, so now when I just did the print line, notice it had all this stuff here. What was going on with that? I've overridden the toString on these movers. Why? Because when we start using them in, we'll have to start using them as arguments to events for the next iteration. And for that, rather than having the default toString, which gives all the parameters, we want, what this is going to be is this will be the current location and the velocity. But it turns out that there's another method there which is called param string, which is going to just print the parameters, what that was. So that's what I'm after. And just want to make sure before we take another step that we have actually gotten our parameters in there. Okay, so now we want to do our path. And for some reason, this should be a 0.2D. Yeah, the wizards at Oracle at some point decided, well, if we're just kind of defining an array on the spot, they don't want to, we can leave this out. And so I can save 8 keystrokes by leaving this out. But in all other situations, if you have to put it in, so it's like, okay, so we just want one. And our destination was -10 and 50. All right, so we're giving it the path, and we're saying true, meaning we're going to start right away. And let's just make sure that that got in there. Why take these baby little steps? Because, and I mean, it just sort of bears repeating because I've seen this in some of the assignments, and I'm not going to point any fingers, but I think you know who you are, where there's a lot of code where some of the early things aren't working. And so even when you're writing one of these components, do it one event method at a time and keep testing it, because otherwise, you have all this code and it's like it doesn't work, but why doesn't it work? This way, it's like when something goes wrong, I know it's because it's something I just did. So I know where to find it. So it goes a little bit slower, but in the end, you get there faster. Tortoise versus hare. Okay. So we verified that. And so what we want is, well, let's, okay, and then our simple property dumper and in the Python one, it's simple state change dumper. Just the true means that in addition to printing the state change, it's going to also print which object it was. And we have two guys here. We have the mover and we have the mover manager. And we want to add this as a property change listener. We're not going to see anything else, but now we want to run in verbose mode. And we reset and we start simulation. And what I'm looking for is, well, what I'm looking for is a validation of, share the whole thing so I can flip between them. Okay, so the velocity was like -10, blah, 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 28 point whatever. And so let's check that out. Okay, where is that going to happen? That's going to happen at the move to event. And let's see. So it doesn't happen. Why doesn't it happen? Anybody know why it didn't happen? Okay, there's something I forgot to do. Well, it wasn't deliberate, but it's still a, remember how these, these work. These work by listening to each other. And I haven't done that. And I forgot to do that. We add sim event listener to the mover manager, and that means the mover manager is listening to the mover, but I want the mover to listen to the mover manager. So now when I run it, okay, that looks a little better. So, but then you're just checking things. So when I start here, the two run events, one for simplest mover, simplest path mover manager. So the simplest mover, our last stop location, check. Velocity, our destination not set yet, and our step move time is 0. And now our simplest path mover manager, our next index is -1, but that schedules the next waypoint. Our next waypoint schedules the move to at our first waypoint. And this is what we're looking for. Our move to the start move event. So here's the start move event, and we see the velocity state transition goes from 0 to -10.533 something to plus 28.0 blah blah blah, and we see that at least up to the, you know, here if I carried it out as far, then they would be exact. So I get check on the velocity, and then second, when did it arrive? Well, the end move occurred at time 2.8480, which was when it was computed here. So, okay, so 1 and 2 have been checked. So now how can we do the, how can we find out or verify where it was at time 2? So for that, we can write a short little inner class to schedule an event at time 2 and just fire a property change with the mover. And then if we hear that, then it will show where we are. So here's how we can do that. Let's see, I might have to make it public. I have to make it static. So I'm doing an inner class check mover. And we're going to extend sim entity base. Got to fix imports for that. Check mover. Let's do check mover. Oh, it says check. Let's do check mover because, yeah, I can't have another class with the same name as a Java thing. All right, so okay, so I'm gonna have two parameters. Time and mover, and then, okay, just to be complete on this, we'll encapsulate that just because we're supposed to have that. And then we have a double time. And then we use our setters. Okay, so now what this is going to notice that there are no state variables. We just have a parameter. What I'm going to do is I simply I can call an event check mover, and I'll schedule it at the time I've said. And Okay, so what I'm gonna do is, I mean, I could do like a print line or something, but instead, I'm just gonna do just fire a property, oops, not an index property change, just a regular old property change. And then all I need to do is just sort of listen for that, and then I'll see whether or not that happens. So let's and so our time at 2.0 and our mover, just to sort of print it, and then all right, so what I'm looking for is at time 2.0, what it's going to do, it's going to fire a property change with the current location of the mover. And remember that the current location is what, on the simplest mover, is what implements, it's this implicit or implied state that uses that equation of motion, this equation of motion, to determine where the thing is at an arbitrary time. And the thing is that in this case, our starting location, the elapsed time, and the velocity, or not the elapsed, our starting time, our starting location, and the velocity, these are all discrete event states. They're constant throughout the maneuver. But this quantity is going to change with t continuously. So if I, okay, so let's sort of check that. And let's sort of run it. So what I'm looking for, well, that doesn't have a main method. Okay, so what I'm looking for is, okay, first our mover there at time 2, after the runs. Okay, here's that check mover event. And so first it does the move to and the start move, and then here's the check mover. And at the check mover, the dumper said, here's the current location of the mover. So at minus 1 point something and 26. And what did we compute? We minus 1 point something and 26. I mean, and they match out as far as you go. Okay. So in other words, this is not sort of an abstract academic exercise. It is something real. Looking at the time, and okay, for the Python folk, I will create another video where I do the same thing on the Python side, just to kind of show you how it goes there. Thank you for your indulgence in that. But now let's move on to what the natural next question might be. Now, let's see, am I sharing? It's sometimes hard to tell. Okay, so basically, the simplest thing is verified both mathematically as well as, implementation-wise. The key ingredient in kind of making this happen is this idea of using the equation of motion to turn discrete event states into a continuously changing state. And in fact, that this has actually, there are lots of other different applications of this concept. And granted, this is a very simple kind of thing, but it turns out that with a little bit of tweaking, we can really do a lot more, just even with this. With a little bit more mathematics, sort of the next thing you might be thinking is as well, the way these things kind of work when you hit a waypoint, you kind of instantaneously kind of change direction and kind of do something. You say, well, that's not the way real things work. I mean, we'd have to kind of slow down, make a turn, whatever. Yes, that's the way kind of quote, real things work. And the question is that in many applications, this equation of motion is more than sufficient to capture the key details of what you're after. So for example, supposing you have a logistics model where there's some operations going on, and let's say that you have different mechanisms of getting the logistics there. So, well, for example, like if you have like helos, well, what is a helo? Well, you would sort of you don't just kind of go full tilt automatically, right? I mean, what is the key element in that? It would be when do the units get their replenishment? That's really the key thing. And so if you're doing this at a distance, the key element is kind of when you get there. Is the key element exactly where the helo is at every point in time, where you have like a 3D model of it taking off and accelerating and then decelerating and landing and stuff? For a logistics model, the important thing is when the hell the thing gets there. And so if it's traveling at an average speed of a certain amount, this model works perfectly fine. Now, if your model is like, I don't know, a dogfight between fighters flying around, this is not going to work very well. Okay, so just no tool is going to work perfectly in all situations. But my experience has been that this actually works a whole lot better than it has any right to in many situations. Why? Because the details, like supposing it's a convoy, with a convoy traveling on roads, and it's a kind of, they start up, they slow down, they have curves, they kind of go up, they go down. But what's the important thing in a logistics model? When do you get the stuff to the people who need it? And so, I mean, if you're traveling in this route, is the key ingredient kind of the speed up and slow downs, or is it like when do you get there? And so modeling it as a constant, say, average velocity, say, okay, we start here, we get there, and so once they get the stuff, then, I mean, if they've had to stop because they're out of fuel, and then we can replenish the fuel, they can start moving again. So that's the important thing in that model. So if we're doing other things, then we don't, you need something a little more detailed. And it turns out we're not going to do it here. Sometimes I torture students with having to do the math for this, but if you really want to kind of take this up a notch, you can, you can, instead of having a constant velocity, you can have periods of constant acceleration, where you kind of accelerate, say, to a cruising velocity, and then decelerate to a stop. You can do all of that. It's just more complicated, and a lot of times the marginal benefit you gain with that, in my experience, is for certain situations not that great. Okay, so it's like, for our purposes, we're going to stick with this for now. But the next question, because as you all know, there are never any answers, there are only more questions. So I mean, what comes up for you when you're sort of thinking of kind of modeling things like this? I mean, what's there should be a little bit of angst, where I'm saying, like, if I'm a unit, I'm going to start moving here and I go there. So it should be easy to think of, okay, if I have lots of these instances of this running around, the event list is going to figure out who's going to land where and at what time. Okay, so that's fairly easy. But there's still something which is probably nagging at your thoughts about this. And what might that be? Well, I mean, okay, we demonstrated that we can identify throughout this maneuver, we can identify where we are at any given point, but it's like, you know, so let's say I'm a truck on a convoy going to replenish something, and what happens if I run into an IED? Yeah, I mean, did I know that when I started? Probably not. um, so so from any, you know, if we're thinking as in the event world, as I hope by now we are, I was expecting to make it there, but I only made it to there because something made me stop. Right. So that wasn't that at least sort of at the nibbling at the corner of your, you know, saying, well, okay, what about that? Well, what's about that is that boils down to modeling detection with this. Can we model detection? And, you know, it's, you know, when I don't know, maybe this is several years old, but it's like, you know, some people get so, I don't know, it's sort of almost a duckling. Like when you kind of do something a certain way, then that's the only way to do it. So like people push back against discrete event because you can't model things that move. And then you say, well, okay, well, here, we can do this. Say, okay, well, you can model things that move, but you can't model detection. Well, not so fast. It's a little more complicated, but it actually turns out to be kind of interesting. So we'll start with the simplest possible case. Because the IED thing, I mean, that really is about a detection thing, you know, so whether something is going to kind of, you know, ding me like that, or let's say if I'm an aircraft or maybe even a missile and I'm entering some radar range or something like that, then it's like, okay, can I detect that? All right, so that's the problem now. The problem that's solving the basic motion problem leads to another problem, which is, okay, how do we model detection? Because if we're doing nothing but just kind of running around and not interacting, then that's not very interesting. We can't create very interesting things with that. And if you think about it, every bit of interaction, whether it's I'm seeing something or whether it's like a weapons interaction, really comes down to sensing something. In other words, the IED needs to sense the vehicle in order to blow it up. The radar needs to detect the target in order to have some kind of countermeasure. Okay, so, all right, let's look at the simplest possible case. So we have a sensor that's located at the origin. It's got like 360 vision, but we're going to give it a maximum range. Okay? And this is something we can, you know, what does maximum range mean? We're gonna take, you know, a very simple idea of that. So when you think of maximum range, you know, you sort of think of beyond that, I can't see anything, and inside that, I might be able to see something. So our basic canonical situation of this interaction is that, say at time 0, we have a mover, and it's going to schedule a start move event, because that's kind of what we're working with. And the start move event is going to schedule some end move event. And so let's say that the mover starts outside the sensor's maximum range, just as an example. And what are the questions that we might want to ask of this? Well, does the mover enter the sensor's range at all? And if so, where and when? And if it does, then does it ever exit the range? If so, where and when? And then, even though it may enter the range, that doesn't mean you necessarily detect it. I mean, you know, when have you ever studied radar and stuff like, yeah, so it's like, there, it's like the maximum ranges are 50%, blah, blah, they're, we're not going to get into that. You can actually get into radar range equations and stuff on this. We're not going to do that, but sort of being potentially capable of detecting and actually detecting are two different things. Because every form of sensing is an exchange of some kind of energy, and that takes a certain amount of time. Even seeing things, I mean, the only way you can see what's up here is because there's light that gets reflected into your sensor, your eyes. The only way you can hear anything is because the energy of the sound goes into your sensors, which are the ears. And then your brain does all kinds of weird things to it. So entering the range and detecting are actually two different things. And so that kind of looks like this. I call this the kind of the canonical sequence for this. So here's our target, and here's its destination. So that's how everything is going to move here. So we have a start move event and then an end move event. And there are 4 events that we're interested in between. And again, we're taking the simplest possible. We have a mover. It's stationary at the origin, and it's got a circular footprint. And I mean, as you know, that the often these are these kind of weird shapes and things. But if we can't do circles, then there's no way we can do the various other shapes. Okay, so what events are we interested in? Well, when does the thing enter the range and when does it exit the range? Those are kind of two questions. And given that it enters the range, when is it detected? And then when does it undetected? Because interestingly, there's kind of going back many decades, there's a huge literature on detection, and at least from a simulation point of view, they're often focused on the wrong question, which is the probability of detection. And in the simulation, that's not as much of interest. What's of interest is when do you detect it, and who do you detect, where, and what do you know about it? That's what a simulation needs. Anyway, so can we compute these things? Well, in principle, we, as demonstrated by what we just did, if I have an event in the example at time 2, I was able to say, okay, the unit was actually at this other weird place that was in between. So in principle, we could do that, but can we actually compute that? And if the answer were no, then we would end a little earlier, but the answer is yes. And we just need to recall one more thing about vector algebra, and that is, if I have the sum of 2 vectors and I want the square of the norm, then the way to do that is the inner product of itself, of the sum as itself. And for inner product, there's a distributive law that allows us to basically unpack it like this. So, in other words, the inner product distributes. We end up like this, and then these are all the things. So how does that figure in? Well, if we started at x and we're moving at a velocity, and this is the equation of motion, then we're going to enter or exit when that location is exactly equal to our range. Remember, the range is this. And so when we are exactly r units away from, in this case, the origin, then that's when it's going to occur, depending. So now we can't unravel this in a nice way. We have to kind of square it. And then when we have squared it, we apply that binomial thing for vectors. And what we have here is, okay, we know what the range is. This is our starting location. This is our velocity. So we have our starting location, our velocity, and the range. We know all of those. What don't we know? We don't know t. And what do we have? We have a quadratic in T. And if you remember in kindergarten, we all learned how to solve quadratic equations. And it turns out that when we do that, it looks like this. So it's minus the inner product, and there's actually an interesting geometric interpretation of this, but this is extremely valuable because this gives us all the information that we want. In other words, notice that there are two roots. And is that something which is sort of reasonable? Is one of them kind of ectopic? Well, if we're looking at our canonic one, notice that there are two times when we're exactly r units away from the origin. One is when we come in, and the other is when we go out. What's valuable about this, now let's kind of look at a picture, and let's look at all the different what are all the possibilities, though? Okay, so this was our canonical example. So we start outside, we go, we hit, and then we exit, and then we're out. That's what we looked at. But is that the only thing that can happen? Well, no. Look, we could start out inside and then kind of go outside. Is that possible? Absolutely. Or we could start out outside and then just be going away. Or we could be starting outside and just completely miss the circle altogether. And, barring tangents, these are pretty much the only possibilities, right? Now, we can't hold a picture up to the computer and say, okay, figure out what this is. Maybe with the new generative AIs we can, but what we have is we have this equation for the roots, and can we figure that out? Well, the answer is yes. If we have two positive roots, then that means that we are in this situation. And then that way we can schedule the enter range of the smaller, with a delay of the smaller root, because the larger root takes us out. If we're inside, that's going to give us a negative root and a positive root, because what that really indicates is that we entered in the past and are exiting in the future. And so in that case, we need to schedule an exit range with the positive root as the delay. Well, what if we have no real roots at all? Well, we do nothing. And what if we have two negative roots? Well, that's the case right here. That's the case where we're starting outside but moving away. Now, and what does that mean as far as the work we have to do? It basically means that in the case of complex roots, or in the case of two negative roots, we don't have anything more to do. And this is where things get interesting compared to a time step approach. In a time step approach, what you typically do is you click the clock by your time step increment, and then you have to check every target and every sensor to see whether you see each other. Do you see me now? Do you see me now? Do you see me now? But here, once I have say if I'm in this situation, then as long as this unit is doing that motion, then you don't have to do anything more. There's no more work to be done until something changes. So, okay, so basically based on the solution to this equation, which is this, if we have two, we're gonna typically have two roots. They're gonna be equal only if there's a weird tangent thing. The likelihood of that is virtually zero. And in other words, you have to, you can create examples where it does that, but in a typical scenario, that almost never happens. But in the implementation, you have to kind of worry about a little bit, but that's just sort of more fussing. Typically, you're going to have a lower root and an upper root, or no roots. So if you have no roots, you miss the range, you do nothing. If a lower is less than the upper, we schedule the enter at the lower. If the lower is negative, but the upper is positive, we schedule the exit at the upper time. And if they're both negative, they're moving away. And so we do nothing. And so the natural question is, well, does this actually work? And as you might guess, it actually does, but you don't have to take my word for it. Okay, so that is that, and so we're gonna start sort of looking at how that is, and then as we progress through this, I'm going to be asking you to start implementing some more things that go beyond the simplest one. So I get to do the simplest one, and I make you do the harder one. Okay, that's it for today.